Okay, so let me know if the screen does anything wonky at any point. Okay, thanks everybody for coming for your final day of EnviroTalks. Erica and I are really excited to be a part of this symposium, and we've put a lot of time into how we're going to be organizing today. So let's just get started. We're going to talk about our careers, our background information on like how we got to where we are, and a little bit of science too. So we hope that you guys will get a lot out of today. So if I can, there we go. Okay. So I like to call myself a landlocked oceanographer. So oceanographer, the ography means field of study. So simply put, I just study the ocean. And I call myself landlocked because I have predominantly lived in the prairies where the ocean is very hard to get to. But that doesn't stop me from conducting any research because I would normally work in a pre-pandemic life. I would normally work in the office with my computer, but formally now I'm just working in my own office with my computer. So I can still study the ocean, even though it's miles and kilometers, whatever away. And then I'll pass it off to Erica.
Hey. Hi, everyone. I'm Erica. I like to call myself a seasick oceanographer. It's a weird field of study for me because I get very sick on boats, but I find it fascinating. So this is usually as close as I get to doing my work, as close to the ocean. Sorry, let me get my door.
She has little kitties that like to come and play on her laptop.
Home time fun. So I like to think about what's going on in the Arctic, and mostly in terms of sea ice and how that's influencing the ocean. So I'm also an oceanographer, and I like to use different types of observations. I look at climate models, and I also like to use a lot of math and physics and drawing cartoons and just trying to get a conceptual idea of what that system looks like and how it's changing. So why don't we go to the next slide? Because you've already heard a lot of words that maybe you're not super familiar with. So we'll give just a few definitions. So let's start with sea ice. So number one, sea ice is just beautiful. This is a great picture that Laura has included from one of her many travels of sea ice. And as you can see, it's frozen seawater. So the ocean is salty, and when it's cold enough, like it is in the polar regions, that water can freeze right at the surface, forming ice, and then you have snow on top of it, and you get these beautiful pieces that cover most of the Arctic, or at least it used to cover most of the Arctic Ocean. And so this is really important because humans and animals will travel on this, and that's important for food sources, for hunting. And it's also really important for the environment because it's so bright and much whiter than the underlying dark ocean. It can reflect a lot of sunlight that was keeping our Earth relatively cool compared to what it is now. And it's also, up until recently, kept the ocean, the Arctic Ocean, fairly calm because it protects it from the wind. So this used to be a very calm region of the ocean with much less waves than the rest of the world. And I think we have a few more pictures of sea ice. Yeah, and we kind of talked about this a little bit too. Oh, this is a really nice fun fact that Laura had added to this slide that I wanted to speak to. One really cool thing about sea ice is when it freezes, it doesn't take all of the salt with it. It just has little pockets of it. And so that makes it relatively even lighter than it would just in terms of ice cubes in regular water. And you can have some really interesting dynamics on that. And I think there might have been one other figure here. Just a few more pictures from Laura's travels. I can't do this. Oh, are you still there? Oh, good. Sorry, my computer did something weird.
Oh, okay.
Oh, it's asking me if I want to update Java. No, thank you.
No, not today.
Not today. Let's go to the next slide and we can just talk a little bit about the changes. So this, most of what we know about how the sea ice is changing is coming from satellite measurements. So we understand really well the change. And this is an image that's derived from satellite measurements showing the September sea ice cover in 1984. And as you can see, it's really extending most of the Arctic. And now in September 2016, already there's a lot. That's now almost 5 years ago. So even since then, the ice cover is retreating. So we're getting a lot more sunlight entering the ocean and a lot more wind starting to stir it up, which is something we'll talk about later. Okay, I think the next bit's you, Laura.
All right. So yeah, just talking more about the different types of ice. Another type of ice is glaciers, and you'd probably see these if you've traveled to the mountains, you would see white caps on top of glaciers. And so glaciers just occur when precipitation is cold, it snows on top of the mountains, and they don't melt away in the summer. So we just get an accumulation of snow on top of snow on top of snow, and we get these beautiful glaciers. So this can happen in cold climates as well as very high elevations. And I just love taking pictures of this kind of stuff because they are just so beautiful. So this is just in BC where we have just this beautiful glacier, and you can see all the motions of it and how it's like been breaking, but this is land terminating. So this is actually, the glacier ends in land. So that's basically what land terminating means. So this glacier, this is actually Mount Robson in BC Provincial Park, actually just ends just before the lake. So the predominant melt force is from the air. The water can't increase melt or anything like that. So it's mostly atmospheric and solar warming that makes a glacier melt. And then one of my favorite types of glaciers is ocean terminating. So that means glaciers, these are glaciers on Greenland that actually end in the ocean. And what's so cool about that is that these glaciers float on top of the ocean, and heat from the ocean can then help retreat and melt the glacier. So that's really, really cool. And they can break off into chunks of big ice like icebergs, and also just more meltwater. So land terminating or ocean terminating glaciers can melt because of the atmosphere, but also the ocean. So there's more complicated processes that can melt ocean terminating glaciers.
Can I ask you a quick question, Laura?
Yeah.
Last one. So those little tiny pieces, those little chunks, are those icebergs, not ice cubes, icebergs?
Yeah, exactly.
Okay, that's
Can you
cool.
see my, yeah, you can see my mouse, right?
Yep.
Yeah. So these are just like little chunks. And then even these little specks, they're called Bergy bits. And that's a scientific term. So you have icebergs and you have Bergy bits. And that's basically just little bits that break off of icebergs. And they're just the bits. So yeah, you can see that here.
And how big are these Bergy bits versus the bergs compared to, like, I don't know, a really big ship like the Titanic?
Oh, yeah, that's a good point. They can be quite small, and they'll actually travel more in packs together too, whereas a big glacier or a big iceberg could probably flow more singular, but these Bergy bits tend to accumulate together. So it would be like you'd have to sum up the whole mass of that little thing.
Like a little melange. That's cool.
Yeah.
Thanks.
And yeah, no problem. Okay, so these are just beautiful pictures of icebergs, and I actually did not take this. This is from a textbook. But what's really neat about icebergs too is that what you see at the surface is not what you see at the bottom, and they're actually much more at the bottom of, or the underside of the ocean. So they can be quite huge, more than what you would visually see at the surface. And these are just more, and they come in all shapes and sizes, so it's so neat. Like you think that there might be sea ice, but then it's actually, okay, no, that's an iceberg. And yeah, they can just be so beautiful. I think photographers just go as close as they can just to get these beautiful photos.
Mm-hmm. Amazing.
And yeah, and there are two sources of these icebergs predominantly, as well as like large ice sheets, which Greenland and Antarctica on the polar, like opposite sides of the world, but they can produce large amounts of icebergs and fresh water into the ocean. So I just wanted to post just two little figures of them so you could see what we're talking about when we say Greenland ice sheet and the Antarctica. Cool. So that's the end of our different types of ice, but Erica and I decided that we were going to kind of do something a little different than your normal lecture. We were going to have just an informal discussion of just us talking to each other and asking each other questions. So we can also invite you guys to ask us questions as well throughout, just entering it into the chat, and we'll keep an eye on it. But we wanted this to be a little bit more fun to hear discussions between the both of us.
Yeah, so are there any questions now on what we've just talked about with sea ice and land ice that you wanted to discuss now? And look, do you need to set up the experiment, Laura, or you're ready to go?
Oh, right. Okay, there is one question. So maybe you could talk to that point while I get my experiment set up. But what Anna has Oh, directly to me. Why do icebergs have a blue tint to them?
Ooh, that's a good one. I'm not actually entirely sure. Do you know the answer to that one, Laura?
I think they're just so pure that light reflects off of it that I think it's just reflecting the ocean. Like I don't think that it
Ah,
would be
so
it's purely blue.
it's kind of the same reason that the ocean's blue, where it's actually reflecting what we see in the sky. And then the question goes to why
Yeah.
is the sky blue? And then that goes to Rayleigh scattering, which is a whole nother physicsy thing.
And I think that's why too, maybe I should stop sharing while I show my experiment, hey?
Yeah, that's a good idea.
Yeah.
And where are you seeing the questions? Is that in the chat?
Yeah, that was a chat, but that was Anna directly messaged me, so that's why I got the notification.
Okay,
So
cool.
thank you. No problem, Anna. Let us know if you have more questions. But I think that's also why, like, when dirt gets into ice, you don't really normally see the clear blue because it's not as pure. So you have
That's
impurities that would then change the reflection and stuff.
Yeah, that's actually a
Okay.
really good point. And that's something biologists have been getting excited about because it can get really like mucky colored too. And that's an indication that there's biology in the ice. But that's moving into an area I don't know too much about.
Yeah, that's right. We like to do more physics stuff.
Yes.
Okay, so this is the first experiment before we go into uh, other things. I'm going to show you the first setup of our experiment. So this is talking about the differences between land ice or glaciers versus sea ice. So what I have here is two different Tupperwares filled with water. This was supposed to be red, but my lab assistant forgot. That's okay. I made my fiance help me out to set this up beforehand. So kudos to him for helping me anyways. So this experiment has a large piece of ice on top. You can see it's on stilts, and this is the sea level here. Whereas this one has sea ice in it. So there's actually a frozen chunk of ice in it right now, like you would see in the Arctic Ocean. And you can see the sea level here. So what I wanted to show is the differences between when a glacier melts in the mountains or on Greenland and it enters the ocean, how the potential impacts it could have on sea level rise versus when sea ice in the Arctic melts, how it could impact sea level. So let's put up the first poll. And what I'm going to do is actually put a heater on this to help the ice melt. And then we're going to go back to this at the end of the talk so that we can see the differences in sea level with the land glacier and the sea ice. So I'm going to put this over, plug in my heater, and maybe we can put up the first poll and Erica can kind of guide people through it.
Yeah. So the first question is, will the land ice melt cause sea level to rise? So that's the one that's on the stilts. And if you're at home, you can put that ice cube. If you have 2 cups of water, you can put that ice cube one on another cup. So it's kind of on a landmass, and the other one just throw it in like you're gonna cool off your cup of water. Okay, so I guess we'll wait for everybody. So there's 28 of us and there's 14, so we'll let everybody answer and guess. Okay, looks like they're slowing down now. People are just changing their minds. Shall we go to the second question? So it looks like it's leaning towards yes, the land ice will cause sea level to rise, but there's some people who aren't sure. So let's remember that bit. 78% to yes. And then maybe we can go to the second question, which is, will the sea ice melt cause the sea level to rise? And if there's any other questions too, while we're waiting for those to come in, we're happy to answer that. Okay. Oh, wow. There's a lot of indecision here. Looks like it's about a 50-50 split for the sea ice. That's fun.
Yeah, that is fun. And we'll talk about that in detail because that can be something that might not be intuitive. So that'll be really interesting to talk about.
I really like the experiments we're doing because aside from the egg one, which I hadn't seen before, I remember like doing this early in my career and getting these questions wrong. So I think it's fun because it's really not that intuitive. Okay, so I'll share the results here. We have like a 50-50 split. And then shall we we'll come back to that at the end and we'll move on with our presentation.
Sure. All right. So I'll go back to sharing my screen.
Okay.
All right. Perfect. Oh, I got the whole, do I just exit?
Yeah, I don't know what to do here. Maybe I'll just press the red X.
Yeah. Okay.
But overall, it looked like 78% said yes to the land melt adding to sea level rise and 50% for the sea ice. So we'll come back to that at the end and see what happens.
Yeah, let me know if you can hear my heater, because I have the experiment over there, heater on the ice cubes, and I have to make sure nothing falls apart. So
no,
we'll
I think you're good. Okay, so yeah, like Laura was saying, we have a nice little collage here where we're just like, let's just put a bunch of pictures about like how we got here, starting at the beginning. And so I think both our upper left pictures kind of gives us our starting point. So Laura, I'd love to ask you a little bit more. These kids might not, sorry, kids, you're high school students, you're not kids, but this movie came out in 2004, right? The Day After Tomorrow?
Yeah, I think so.
They might not have heard it before. Do you want to give just a little quick summary of what it's about?
Sure, yeah. So this movie takes climate change to the extreme level. Like, it talks about the scientist, Jack Hall, who is a paleoclimatologist, and his job, essentially, like right away, he's jumping over crevasses. Like, he's being such a bad, like, really cool person. Like, he's just being like super intense. And then later on, he talks to the government about climate change, and he's trying to like make changes, but then things are being slow in the government and not fast enough. And then his son is caught up in a disaster, and he has to go save his son, who's Jake Gyllenhaal. And
it's the classic like end of the world movie, right? Like things are ending, but
exactly.
I saw this picture on your thing, and I was like, I'm gonna prep for this and watch this movie because I hadn't remembered it from so long ago. And I looked at it and I was like, wow, when is a climate science kind of like at the center, like the hero of the story? Like this is so amazing. I can see why it would have an impact on you. And my curiosity, and then I saw a lot of things that I thought of you because he was working on the polar regions, and he's a climate scientist, and he's going to places, but he's also working with computer models. And like, which part of that really spoke to you as a seventh grader? I guess you were.
Yeah, exactly. So I was in 7th grade when I first saw this, and at that point already, I was already like a little environmentalist. Like, I was thinking of ways to like volunteer and like save the trees and like doing just like fun volunteering stuff. So when I saw this movie and there was this guy who was this crazy passionate scientist who then got to speak to the government, I was like, I want to do this. Like, this is amazing. And as a kid growing up, I always spent times with glaciers. Like, I was always hiking with my family, and we'd be camping. Like, this was a trip like over 10 years ago, but I'd always be camping and seeing mountain glaciers and camping and going into the ocean when I was really young. So I always knew like I wanted to do something in the environment, and seeing this job, I was like, that's it. That's what I want to do. He is doing something that seems so important and so key to like what the future could hold. And I was just so inspired. By grade 7, I was like, I want to be a paleoclimatologist. I have no idea what that word is, and I don't think I knew about it until later in my undergrad.
But you knew it was kind of like that pie in the sky, like I want to go to there.
Yeah.
That's fantastic. So what were like the first steps to doing, like you knew you were into it and you were interested, like what's next? What's the very first step?
Yeah, so the very first thing I started doing was telling my teachers. Like, I didn't know anything about paleoclimatology. So I just started asking my science teachers, being like, this is really cool. And I remember having a conversation that really impacted me was in grade 12 with my physics professor or physics teacher, who was so helpful about careers that I remember being like, I want to do paleoclimatology. And he was like, wonderful. Like, that's going to be so important. And he was so encouraging that we kind of had more conversations about what kind of career or what kind of undergrad I would need. I had no idea that I would need 10 years of schooling, but at first it was like, okay, this is what I'm interested in, so let's do an undergrad in there. So I applied to different universities, and I ended up going to the University of Alberta in Edmonton, Alberta, and I did an atmospheric science degree because at that time, that's what the university was offering for climate sciences, I think at that point I would have joined anything in climate, but at that point the U of A only had an atmospheric science program. So then I started a 4-year program. So that's what I started with after having wonderful conversations with like high school teachers, just asking questions, being curious, like I don't know how to get here. What do I need to do?
How do you do
Someone
this?
pushing me along the way. Yeah.
That's wonderful. I also had a really good experience with my high school teacher, but in such a different way. I was really struggling with my high school physics class. Like it was that one class that I was just like, it was not making sense to me. And I remember that kind of got me really awakened and like into it because I was like, I want to understand this. And I got a little book to work through. And I remember one of my friends found it and he opened it and he was like, it looks like you're arguing with the textbook. And it was true. I just felt like nothing makes sense here. And I was arguing with it. And I had this very patient high school teacher that was willing to sit down with me and kind of slowly explain that, nope, it turns out that Newton got it right. And like, get people moving and all these things.
And you're just like, I don't get it. Like
I was like, no, this doesn't make sense. I was very like, this is wrong. And he was like, let's work our way through it. It was very patient with it.
Oh, that's so great. That must have been so helpful to like allow yourself to keep asking questions and not just assume, but to be like, well, why is that right?
Yeah, I think that was part of the beauty that of science that was kind of occurring to me then a little bit, even though it was not yet my focal point like it was with yours. I think I was appreciating the fact that you were allowed to enter something and say like, I don't get this. I don't think this is right. And it's a form where you're allowed to do that. I think like in other parts of life, there are these rules that we kind of just like, even if it doesn't make sense, let's just do it and we don't rock the boat. But science, it's like rock the boat. It's all about rocking the boat. So I started to get a taste of this a little bit.
Yeah, could you talk more about what got you into, I guess, where you went after high school and why? Like I'm seeing
Yeah.
all these pictures here and I'm kind of wondering, like I see dinosaurs, I see ocean, I see stars.
Yeah, what's going on here? This is some
Yeah.
craziness. So I'll start with my top left, which is so even I was enjoying my physics class a lot, but my entire life was revolving around tennis at the time. And I'm from Albany, New York, and I got a tennis scholarship to play at a university in upstate New York. And that was my whole
Wow.
life. Yeah, this was me as tennis, everything, everything, everything and this is what this ice cube is about. In the middle of winter, I slipped on some ice and I broke my foot. And long story short, that was the beginning of the end of my tennis career. And I couldn't play for quite a while. And I started to get really obsessed with physics. I was enjoying my textbook and reading and being confused. And that slowly, I again had a professor like you who was just really helpful with me and pointing me to, and this is helpful for everyone here, undergraduate internships, which was just like a world I didn't know anything
Yes.
about. But you can travel by undergraduate internship. Like I was just basically in New York 24/7 unless I was going to a tennis tournament. And all of a sudden, this professor kind of guided me through the application process, had me apply to gazillion places, and I got to travel to California for the first time. So that's that picture on the bottom left. And that brought me to Woods Hole, Massachusetts, where I started to learn about fluid dynamics, and then later astrophysical fluid dynamics in Santa Cruz. I went to Australia. That's where that beautiful picture is from, along with the kangaroos, and did a lot of
Wow.
astronomy. And then finally, at the bottom right, I got to work in New York City at the Museum of Natural History. And it's a really weird kind of roundabout adventure, but through these different internships, I really loved the one here on the bottom that's actually showing a picture from my first publication on astrophysical fluid dynamics. And it turned out we were studying a phenomenon that started in the ocean. It started as a lab experiment to try to understand ocean physics. And I realized we were just kind of turning the parameters a little bit, just enough to start to understand how the same mechanism could apply to astrophysical systems. And it
Wow,
was
there's so
really,
many.
there's a lot like, blah. Here's everything
Yeah,
in a nutshell.
there's so many things in there that you said that are so cool. Um,
It was fun. It was fun.
like I had no idea. Like we've known each other for a few years, but we've never had this kind of conversation. So we were both so excited to be like, we're gonna ask each other how we became to where we became, because that is so neat that I didn't know that you went on tennis scholarship to a university, which is like so cool. But
Mhm.
then how you also dabbled in so many different internships that kind of covered different aspects to kind of just
Yeah,
figure out.
and I think that's really helpful, like for students going later, like I kind of jumped all over the place. And I think I remember a professor even suggesting this to me, like, early on in the beginning, it's almost like dating, like just try a lot of things on, see what you like, see what fits, see what feels good. And slowly you'll kind of start to form that thing that really gets your curiosity going.
Yes,
And,
yeah.
and so that was true for you too. You started to do these different internships as well. That was during undergrad too?
Yeah, exactly. During my third year of my undergrad, I asked a professor, like, hey, do you have summer work? Like, can I work for you in the summer? Like, what does that entail? Because I kind of heard people doing that, just approaching their, like, after being taught a lecture that, and you really like that professor, just to
Mhm.
have a conversation to them and ask them, like, do you have any opportunities for summer work? Because guaranteed, they probably do. And if not they might be able to tell you about a program or somebody else. So always ask people questions about opportunities.
I agree.
And that was
Become
like my
buddies with your
first,
professors. It's great. They
yeah,
want to help you, and it can really open a lot of doors. Sorry, keep
yeah,
going.
exactly.
Tell me
No,
more. So, what
yeah,
happened? You got to work with them. What did you do?
it was very, um, I, okay, I was looking at like monsoons and
Mm.
like it was very like monsoon precipitation amounts and the shipping industry out of India and how it was like related and correlated. So I was trying to do stats on, yeah, the monsoon index and shipping. So I had no idea what I was doing, but it was so much fun. I was getting like really old books about like shipping industries and like the 1900s and whatever, and it was just I
That
didn't
makes
know what I
sense.
was doing.
Me neither. That
And
was my whole
yeah,
experience. Was I feel like this whole period of my life was just like I don't really know what I'm doing, but man, I'm so interested. You get to just follow your nose for a while. So what happened?
yeah,
What
and
happened from there? Because you didn't stick with monsoons. You went further north.
no, yeah, exactly. Um, During that time, I was speaking with another professor, and he mentioned how I could do an undergrad thesis. So that means that I get to do, I think it was worth 2 university course credits, and I got to do research throughout the whole year. Then I would have to write a report. So I got to work on ocean modeling, very applied, and it was very helpful. Like it was very educational into what research could be like. And he essentially, this is Dr. Paul Myers at the University of Alberta. He essentially let me pick interests that I had, and it came from a class as well where I read a paper and I was like, oh, I really like Greenland. I love glaciers and I love the ocean. Like those were still passions of mine that I had as a kid. Like that's why my pictures here, it's all about the ocean for me. Like in my first time surfing to like later surfing and like just being by the mountains and the like, I was like, I love this stuff. And if I could study it, that would be amazing. So, and then also with Jack Hall, I was like, okay, like how can I combine these worlds? And yeah, so it came from there. And essentially, my undergrad thesis what got me so excited about looking at Greenland melt in ocean models and how the melt can affect like the Labrador Sea. And just this is a very important region for lots of different factors of like ocean mixing, temperatures, biology. So it was really cool. And that actually led me to do a master's with the same professor because I was like, I love this. This professor and I got along really well. And I feel like that's super important. I know this is like so far ahead for people right now. Like you're just looking at undergrad, but when you're looking at internships and masters and PhDs, your relationship with your supervisor or professor is so important. And my professor and I got along so well that I was like, this is so cool. And it led me to really cool opportunities too. Wow, like not just the research, but also just life experiences.
I totally agree with that. It's amazing. And I feel like it can happen naturally. Like, I felt like though professors who were reaching out to undergrads, they really have their heart in a good place. So it's a really nice time and a good way to meet people. So okay, we're gonna move towards our next experiment. But before we do that, Laura, do you want to talk about what your favorite or most difficult project was during this time before your PhD?
Oh, okay. Actually, the one that was my most, it was actually during my PhD, but it was like one of my second projects. And I dealt So normally I look at the Greenland ice sheet and its impacts on the ocean in an ocean model, as well as ocean heat on the Greenland ice sheet. So those are basically it's a two-way connection, and that's mostly what I focus on. But throughout my PhD, something took a left turn, and I was like, oh, I have to follow this through. So what I ended up doing was looking at the Labrador Sea, which I was talking about before, which is a huge part. It's really, really cold there. There's lots of winter storms, and this creates huge mixing in the water column. And it's really important for models to get this mixing and this stratification, how layering of the ocean works in an ocean model, because that can have huge implications in large scale ocean circulations, biology, just the world. It's very, very important, these big ocean currents. So
it's true.
project was kind of new to me.
Right, you're speaking to the overturning circulation, right? When you're speaking of the Labrador Sea, that's when you get the really big convection events that they talk about in the movie. What was, The Day After Tomorrow. Sorry, I had a little question about it. Like, sorry, continue.
No, yeah, exactly. They talk that, like, The Day After Tomorrow basically talks about this huge ocean circulation shutting down, and Labrador Sea is like one of those places where this could potentially happen. So stratification in that location, layering of the ocean, is really, really important. And that was kind of like my hardest project, but it was most funnest because I felt I learned a lot out of my comfort zone.
That's cool. Yeah, and so that kind of brings us to stratification. And actually that was my favorite and most difficult project too, was very related to this stratification, this idea of basically in that little picture we saw there, that was a study of looking at warm salty water sitting above, cool fresh water sitting above warm salty water. And so we're going to talk a little bit about that in stratification now in the next couple of experiments.
See that we have two questions in the chat.
Yeah, let's get to the question.
Okay, the name of the movie, I'll just type it in, Day After Tomorrow. And I recommend everybody to watch that because I loved it. It's very extreme. Like, it's very extreme what happens, but it's really, really fun. And then,
okay, Jake Gyllenhaal is so little.
I know, he's such a baby in that. So cute. Oh, I had such a crush on him too. That's yeah. Like, so I was like, oh, I love him. Okay. Stephanie asks. Okay, Isabella's seen it before. Nice. Okay, Stephanie asks, yes, that's really cool. I learned about the URA and USRA award by approaching my professor.
Oh, that's fantastic. Yeah, it's such and there's a lot all over the place. The ones in Woods Hole, if people are interested in oceanography, Google Woods Hole Oceanographic Institution. They take international students. And if you're interested in astronomy, it was the Australian, well, that I'll have to remember because it's been a while now. It's like 10 years ago.
Yeah. I just want to quickly say too, what I really loved about, well, and I guess we can talk about later too, but I love how you were doing physics and you did atmosphere, like astro, and then you got to ocean. But I can't wait to ask you more questions about that later. But we'll let you do your experiment.
Oh, sorry, and I have one question. It went direct. I don't know if I can answer it. Which type of ice melting has a larger impact on biodiversity? That's interesting. So I guess it wouldn't be which type. I don't know. Do you have an answer for this? This is, again, a little bit outside of my range, but maybe you have a good idea of it.
Oh, that is such a good question. And take that question and go study it and do a thesis on it. Like, that's so important.
Let us know.
Yeah, because like glacier melt changes the fresh water, changes the composition of the water column, and that impacts primary productivity. Sea ice melt also impacts primary productivity. So when you're looking at the food chain, the really, really small part of the food chain, the first step, is getting impacted by changes of fresh water from sea ice, from glaciers melting, and what else?
The light too,
even
right?
Icebergs.
Oh, I was just going to say
light. Yes, light.
Because the sea ice is blocking the sunlight from coming in, and so that's going to be important for primary productivity as well.
Yeah. And large mammals will go where they can either hunt or take breath when there's breaks in the sea ice and stuff. So I couldn't tell you which one's more important, just that they're all important.
Yeah, exactly. All right, so let's get to our next experiment. So hopefully, I think you guys were told we were going to use a few different things. So this is going to involve, first we're starting with 2 fresh cups of water, about the same temperature, and I'll just stir them up so they're well mixed, as we'll say. And in one of them, I'm gonna add a whole bunch of salt. So these are like mason jars, to give you a sense of the size. And these experiments, you'll get different results depending on how much salt you use, but roughly the same idea, you'll always see that. So I'm gonna go ahead and add about 3 tablespoons of salt, I think were what was needed for the egg experiment, right, Laura? Am I remembering right?
Yeah, maybe add an extra one just in case.
That's gonna give us so much stratification for the next one though.
Yeah,
Let's see if this one will work. Worst case scenario, we add one more later. Oh, and I thought I'd add just a little bit of dye too. I have some food coloring, if you have that at home. I don't know, it's just kind of nice because we're gonna later add ice cubes, and so it'll remind us that this water is a little bit warmer than the ice melt. So I'll just stir that in too, so we have some reddish here. Okay, cool. And now we have a couple of eggs. Oh, poll. So what's the next poll question? Right, which egg will float closer to the surface? The egg, we're gonna put an egg in each of these. So will you be closer to the surface in the fresh water, salt water, or the same? Okay, let's see. Okay, we've got a few in each.
Okay,
looks like the salt water is winning. Okay.
Everybody get those votes in.
Yeah, get those votes in. We'll give you a couple more seconds. Oh, there's some wavering. It looks like the salt water is winning out. All right, cool. Let's share the results. Good. I'll just exit out. Okay, let's see what happens. So take your egg, and these are raw eggs, so we want to be really gentle here. So you want to just put it on the spoon and let it kind of go where it will. So there's the fresh water going straight to the bottom. And then, oh, sorry, there's a bit of water in that cup and I just poured it on me. Okay, here's the other egg, and that's going in the salt water. And that one's going to the bottom too. Oh, let's stir it up. But you guys are right that the egg, if we get enough salt in here, then we're basically changing the buoyancy of the fluid. And so that should allow the egg to float. Oh, I think it is floating. There we go. Just had to stir it up a little bit.
Mixed.
Yeah, exactly.
Do you mind sending your camera angle just slightly down a little bit so we can see more of the, yes, perfect.
You guys see that okay? And I can put my little whiteboard up too. So you can see this one's surely at the bottom, and then as this one moves around, it's floating on the top. And you guys are exactly right. This one is floating. And the reason is as we add salt, we're adding mass to the fluid, so it's becoming heavier. And since it's heavier, the surrounding elements are heavier, it can float, whereas in this one, it's lighter, and so it sinks to the bottom. Okay, so now pull out your eggs, pop them somewhere safe. Try not to crack them if you can. Not make any more of a mess than we're already making. And then, Laura, do you want to explain the next poll, and I will grab my ice cubes.
Yeah, okay, let's pull up that next poll then. All right, so now Erica's going to be putting in ice cubes into both containers, and the question is which ice cube will melt faster? The ice in fresh water, the ice in salt water, or the same? So this one's, yeah, okay, interesting. Get your votes in because this will be really, really fun to discuss. So, yeah. Come on, everybody, get that in. So, yeah, we're getting 65% of ice and salt water, a little bit more. So,
yeah, it's interesting. So I'll say the first time I saw this experiment, my first thought was I'm from upstate New York, and I know that I put salt on the ground to melt that ice in the winter so we can drive around. So my vote was for the salt water. It looks like most of your votes are for the salt water too. I'm going to show why we were both wrong. It's actually going to melt a lot faster in the fresh water. So, okay.
This is so cool.
This is so fun. It's so fun. Okay, so I got a couple of ice cubes here now, and I'll just mix everything up again. So we're well mixed fluid, and I've used coloring again to make it green. Oops, sorry, I have the little hole in front of me. There we go. Okay, so first let's add it to the fresh water and see what happens. Okay. I'll just pull this up so we can talk about it. So do you guys see these little filaments coming down all the way to the ground? Look at that, all the way to the bottom.
You can see those green pieces going down. Yeah.
Yeah, hopefully you can see it well. So what's going on here is that the ice cube, that meltwater, is colder and therefore it's heavier than the warm fresh water below it. So it's sinking to the bottom, the warm water is rising up. So you're getting a lot of mixing with the warm water below. This is just like when you boil a pot of water for your tea. It's convection, you're getting that mixing. Now let's add.
Erica, you said you're adding cold fresh water and warm salt, and the ambient, the existing water in there is warm and salty.
Sorry, warm and fresh. This is warm and fresh. Thanks for reminding me.
Oh, okay.
This
okay,
is the
warm
fresh
and fresh.
one. Yep, this is the fresh one. So it's mixing with the warm water below it, right? Because we're just dealing with temperature on this one. So you're just getting good old regular convection. Okay, and that's getting really dark because you're getting all that mixing. Now we're going to add
cold water. Oh, sorry. So then cold water is heavier than the warm water, so that's why it's sinking down. Cool.
Yeah, that's exactly right. Okay, so now let's do the same thing, but with the salt water, and we'll see what happens. So we're still getting some pluming, but it's already looking a little bit different. It's not reaching the bottom. So what's happening here is that, yes, still the ice is cold. The ice melt is colder, but it's also fresher than the warm salty water. So you have the salt taking effect here. So this is kind of leaving, creating this little salt freshwater lens right at the surface. So we have a lot of salt here, so it's sticking right to the top. Depending on how much salt we put in here, you'll see this interface at different levels. Whereas if you have less salt, then that can start to drop more, and more salt, it sticks to the top. So what's happening is we're creating this freshwater lens that's going to protect this ice cube from the warm salty water below it. So, well, oh, you can almost see now. I'll try to turn my computer up. This ice cube is actually almost gone. I know I put them in at different times, so that wasn't really fair, but we'll come back to this at the end, and I'll show you that the saltwater ice cube is still there. You can check at home and play with this, and you'll see the same thing.
So then, Erica, is this something that you look at with your current research?
Yeah, absolutely. So this might just seem like we're talking about cups of water and who cares, but it turns out that this cup is actually surprisingly like the Arctic Ocean. So in the Arctic, you have a lot of freshwater sources at the surface from ice melt, from precipitation, so rain and snow, but also river runoff from the continents nearby. And so that's always supplying a lot of cool fresh water at the surface. Whereas on the bottom, you have waters entering from the Atlantic and Pacific, and those waters are warmer and saltier. So as they enter into the Arctic Ocean, they're subducting below that cool, fresh interface and sitting below the sea ice in the Arctic Ocean. And that turns out to be really important because there's enough heat in those waters that if it were brought up to the surface, it could melt all of the sea ice. And so there's a lot of Arctic oceanographers that are trying to understand this sort of mechanism, how it's changing as we're losing sea ice, and what it means for the heat that's being stored at depth. Yeah.
So cool.
Yeah, and you're studying this stuff too, right? You were mentioning stratification in your last project.
Yeah, like it's so interesting how we can be studying two different things, but the science and the physical processes that are in the ocean are so important to both. So like, yeah, the mixing of the water column, having warm waters brought to the surface can then impact like the glaciers that are terminating into the ocean. It can actually help them melt even more. And that's why sometimes like in 2012 and 2016, you have really, really warm years of these glaciers melting so much, and these warm currents are actually going along the coast and increasing melt. So yeah, very important. Very cool. Should I share my screen on the...
I think we have, we have a few cool pictures about how we study this stuff in our research. Are there any questions before we continue? It looks like we've got everything so far?
Yeah, I think so. But yeah, feel free to just keep asking us questions.
Yeah.
Okay, I can. All right, so this is all of the different types of tools, and not all, some of the different types of tools you can use to look at Arctic science in the ocean. So cool. Erica, I see like so many different things on your end here. So this side was Erica was like, I'm just gonna put things that I know, and I put things that I know on this side, but we both kind of deal with a little bit of both. Can you speak to maybe surf? Because I feel like that's a very important gem in Winnipeg.
I think that's a great one. So yeah, this surf, it's called the Sea Ice Environment and Research Facility. Gosh, I hope I got that right. It's right at the University of Manitoba. And I'm not sure if you can tell, but basically it kind of looks like a hotel-sized swimming pool that's outdoors, but with a lot of equipment set up on it. And in the really cold winters of Winnipeg, those waters freeze. So we fill this pool with salt water, and that surface is going to freeze and create sea ice that scientists can study. So this is one area that I'm hoping, it was supposed to be last winter, but COVID happened. So hopefully next winter, I'll be there looking at similar processes as we've discussed today in these cups of water. Yeah, and what about you, Laura? Let's go to one of yours. Perhaps ocean models. That's your bread and butter, I think, right?
Yeah, that's my jam. That's right. So this picture here is just the colors are just showing the region of where I look at, or where my ocean model calculates how the ocean behaves. So models are really, really neat. Like if you think of even a weather forecasting to tell you what the daily temperature is, they use models to help predict that. So you have to have some underlying physics and math and also some type of observations to help force these models to then study the nature of the climate. So in an ocean model, I predominantly just look at the behavior of the ocean. And for me, I only look at the physical side of things. So I look at temperature, salinity, the motion, so the velocities and the accelerations of fluids, but I don't look at the biology side. And if you love biology, you too can study the ocean using a model. I have a colleague and she's a marine biologist essentially, but she looks at ocean models and
Right.
she studies primary productivity. Where is it, like the life of the ocean? Where are they in an ocean model? So even though I do the physics side, you can do so much with an ocean model. So they're really, really great. And
That's
also
a really
they,
good point, because like we were talking before, how in oceanography, you find people from all sorts of backgrounds. You can have people that are coming from the geophysics side, chemistry, biology, physics, engineering. We can all come together and study the ocean and the climate, the atmosphere, and science in general. You find us all here using a lot of the same tools.
yeah, it actually, this is kind of an aside, but for you, your undergrad, you did an undergrad in physics, right?
Yep, that's right.
Yeah, so then, and we differed because you did an undergrad in physics and I did an undergrad in atmospheric science,
That's right.
but you're learning all the same tools. Like
Right.
having that underlying knowledge, you were applying it to astro at one point, correct?
Right. Yeah, I guess in the
Yeah.
sense we're both looking at fluid dynamics, because you find fluid dynamicists trying to understand stars and planet formation and the atmosphere and the ocean. So we brought those tools to understand the Arctic Ocean. Yep, that's totally right. So let's do a few
Oh,
more of
cool.
these before we go back to your experiment. Do you
Yeah.
want to talk about the Argo float?
Oh, sure. Yeah. So one thing that's really neat is that an ocean model, I always talk about ocean models, but they give you such a wide region of model data.
Mhm.
But observations can be limited just because you are literally throwing a tool in the ocean and you have that location at that time. But they're
Mhm.
so useful to help validate, is your model doing it right? Can we make our model more correct by having observations? So Argo floats, actually, Erica, I would like to have you talk about these Argo floats because I think you actually know more than me. I come from the modeling side where I appreciate the observations from Argo, which is a huge network of observations, but I'd love for you to give some more insight.
Yeah, so these things really changed oceanography for us, because for a really long time, most of what was collected were on through ships. People would go on ships and collect these data. And like as Laura was saying, that's only one point in time in space. But now we're putting these Argo floats. They're all over the ocean, and they're drifting through the ocean. They're automated, and so basically they have this little bladder that changes their density. So when the bladder expands, it's lighter, it comes to the surface. And as it moves to the surface, it's taking measurements of temperature and salt, sometimes biogeochemistry. When it reaches the surface, it'll send the data just like we send a text message through satellite. And then that bladder goes back and it sinks to a predetermined depth, and it'll just float with the currents for the next 10 days until it comes back up again. And we actually have a really similar, so this is really tricky to use near ice. Basically, as soon as you go to the Arctic, everything gets harder because there's ice and ice breaks instruments. And if the ice doesn't break the instruments, the polar bears will.
Yes.
So there's this thing that in oceanography in the Arctic, we're about 50 years behind everyone, which is fun because we're still kind of in that Wild West area of the study where we still don't really know how it all works. But now we have these ice tethered profilers shown here. And that's kind of our Argo, where we have these instruments that are frozen into the ice so they can't get crushed by the ice at least as easily. And then there's this little instrument that it's attached to. It runs about 800 meters down through the ocean. And there's a little instrument running up and down that line 3 times a day, taking measurements and sending it back to us via text message. And so I'll just speak to one last thing here, these ice camps. This is another way in the Arctic that we got ocean measurements way back in the day. So this is a picture from 1975 where scientists lived on the sea ice for an entire year, drilling holes and taking measurements below the sea ice by hand. This would be impossible in that region now because we don't have sea ice. So luckily we have these ice tethered profilers that are telling us how the ocean is changing. And with that, do you want to go back and we'll check on your land ice and sea ice experiment?
Yeah, let's. So that heater's been going on this whole time, and my room with the sun now is getting quite warm.
Okay, good.
So I'm gonna just bring it over.
Okay, and let's see, we don't have any new questions yet, but I will just remind everyone, our guess was 78% of us thought that the land ice melt would cause sea level rise, and only 50% thought that the sea ice melt would cause sea level rise. So now let's see how it all turned out.
All right.
Oh, this is fun.
So, I know. So because I'm doing this from my bedroom, it's so funny. I have Tupperware containers on top of a chair just so I can get the right height so that you guys can see this. But I'll also bring this a little bit closer so that we can.
I love it. Yeah, right. And let's not like douse our computers with water.
Ooh, it got so warm by the back here.
Oh, wow.
I melted the Tupperware a bit. Okay. So this is my land glacier in my stilts. So you can see that this glacier was above the water, and maybe I should have just kept it still so you could see the level.
Yeah, I think even back there we can see it well, the sea level change.
Yeah?
Mm-hmm.
Okay, so we started with it being here, and then as this glacier was melting, it increased the sea level. So everybody, you were correct. When glaciers melt, they add mass into the ocean, and the sea level rises. And this is huge because on Greenland, there's about enough to change, is it 7 meters? And then Antarctica's 50, or yeah. Which is that seems like maybe not enough, but when you think of coastlines and you go and you visit the beach and everything is so flat, it doesn't take much to just
totally flood
fill up the coastline.
Mm-hmm.
Yeah, so that's why it's so important to look at Greenland and Antarctica and mountain glaciers. One, they're a source of fresh water, which is very important, but then also they can change ocean circulation and sea level, which is really important. Now, when we look at the sea ice one, when I move this floor isn't completely level, so that's why maybe there's a little bit of a slant. But this ice cube, when it started melting, it didn't change the sea level because the ice was already in the ocean. So sea ice does not change the sea level directly by melting, but there are other implications with when sea ice melts. Changes in albedo, changes in heat source to the ocean. Erica, can you think of more about the implications on sea ice since it doesn't cover sea level or doesn't?
Yeah, so I think a big one, which we hadn't spoke of, and maybe we can both speak to this now, is the wind. So when you have sea ice covering most of the Arctic Ocean, as we did back in the 70s, that's protecting wind energy. And as we know from going and visiting lakes or the ocean, when you have a lot of wind, you have a lot of waves, and that can really stir things up. And so when you stir things up, then you can start to interact more with the warm, salty water below it and bring more heat up. And as you bring up more heat and have more energy, that's also going to influence flooding because you'll get more waves crashing into the coastline.
So then let's put up that next poll and see. Yeah. Okay, so we'll answer the next question, but after we
Is
do
that
this
a poll
poll.
question? Let's see.
Yeah.
Oh,
Yeah.
I thought it was a Kahoot. I messed it all up.
Okay, that's okay. No, that's fine. Hopefully then it'll be more obvious. So what force could cause warm, salty water to the surface and melt ice? So yeah,
Sorry, guys.
we're seeing, no, that works perfectly because then that means they learned what you were saying. So that's great.
That's good.
Yeah,
Oh, this is
good.
kind of a tricky one because in a way it is also sea ice melt, isn't it? Is in the way
Oh,
we
that's a good
explained it.
point. Okay, that's actually a really good point, guys, because it's all connected,
All
right? Like as
connected.
sea ice continues to melt, it exposes more ocean, which then wind can stir it up and make more sea ice to melt. So you
Yeah,
have that feedback.
we do have that feedback. Oh, but nobody guessed Poseidon. I guess everyone's paying
Ah,
attention.
yeah, I know. We thought that was fun to throw that in. Like, what's the god of the ocean again?
Okay, so
Awesome.
shall we go to our wrap-up slide? We're about 3 o'clock here.
Okay, we have one question, and maybe this
Oh,
will.
yeah.
I was curious to know how much other fields of science influence your research and your education. I know Erica mentioned using physics, and I suppose Laura uses computer science for ocean models. Can you talk about what areas surprised each of you during your studies? Yes.
Ooh. Why don't you
Yes.
speak to that?
Yeah, I had no idea starting my degree that computer science would be so important. I still don't call myself a computer scientist because I don't know, for me, I was like, that's not where I came from. Like, it was so funny. That was so surprising. I did not expect as much math and physics and computer science for what I'm doing. And now I'm an ocean modeler. And that was so surprising to me. Also, a little bit of geology for me, because I really like glaciers. And to study glaciers, you need to have a background in geology and land formation. So geography too could help as well. And Erica, what was neat with you, you did physics undergrad, but then you went to a master's of engineering in mechanical, and
Yeah.
then you went back to physical oceanography for your
Oh,
PhD.
well, that was a little bit of a trick there. So I actually entered the physical oceanography program at Scripps. But I realized after doing the coursework for a physical oceanographer, if I just took a couple more fluid dynamics courses, I could call myself an engineer. And I felt that was important, actually. Then this speaks to what surprised me because I thought, well, what's going to be on my transcript is oceanography. And me personally, when I heard oceanography, I thought, well, that means like marine biology, like playing with dolphins and stuff like that. So I was like, let me try to get that engineering degree in there. But yeah, that was the thing that really surprised me. I still remember I was in San Diego doing astrophysics for my first internship, and I was applying to the next round, trying to see where can I go. And somebody said, "Why don't you apply to Woods Hole?" And I thought, "Stop making names up! Like this place doesn't exist. What is a Woods Hole?" And then that kind of brought me to learning about just the existence of this field and the fact that there are a lot of mathematicians and physicists that are working on understanding how the oceans worked. And I felt like as a physicist, I was mostly geared and pushed towards understanding that I can use this knowledge to look at astronomy or particle physics. But when I learned that this is something we can do in the ocean and it has these real world consequences because it's related to climate change, that really blew my mind. I hope that answers your question. If not, please ask more.
Yeah, I like Jack's comment. I wanted to do Poseidon as well. Yeah, I think that's so interesting because you could, like, I came from it studying atmosphere to then apply to the ocean, and university physics classes didn't go well for me. I didn't find it interesting, so I didn't study hard in those classes. So for me, I only did well in the applied environmental classes. And I know if you enjoy something, follow that route and you'll just like keep going that way. Like, yeah, you could have a background in physics, you could have a background in engineer, you could have a background in atmosphere. Like if you like fluid dynamics, essentially it's all the same. It's just the time scale. Like geophysics, it's like they're looking at like land formation and how earthquakes happen and like lands going on top of lands, and it's all motion, but it's still
Slow.
geophysical fluid dynamics. Like it's all the same.
Yeah, that's
Yeah.
such a good point though, because it's like we all, oh, that answered it. Okay, good. Um, yeah, no, I think that's such a really good point though. We all come from really different areas. And I think to your point, Laura, like I found in my classes too, if I wasn't interested, I didn't really do well. But it was amazing to me. Like, I remember in physics, I didn't really like thermodynamics. I found it super boring until I needed it to understand my geophysical fluid dynamics. And then all of a sudden it became really interesting and I wanted to understand it. And then I do well in it. So, to your point, I totally agree. Like, just keep following the thing that you find confusing and interesting and makes you really curious. And that'll kind of battle down the other barriers that you run into.
Yeah, and it might help you too, like asking your professors, being like honestly, why am I learning these math equations? Like I don't understand how this applies to the atmosphere. And they can be like, oh, let me tell you, by the time you get into your fourth year or whatever, like you'll be using this.
That's true. Yeah,
Um,
and I think that's what's great
yeah.
about these fields is I think professors even really enjoy that. Like you go there and like, why are you teaching me this? You know, they won't be offended. They'll be like, good question.
Yeah. Should I go back to the PowerPoint? Oh,
There's
are there
one
any physical
more.
skills?
What kind of physical skills do you need to do oceanography? Oh, so many physical. I guess in terms of like physics and equations, or do you mean like being strong?
Yeah, good question. Physical in what way? What do you mean, Isabel?
They're both good questions. I
Yeah,
guess. Well, let's try to answer
like
like the
body. Okay.
body. Okay, that's what you meant.
I guess it
So
depends on what kind of physical, like what kind of oceanographer are you? Are you diving? Like there, I know a
yeah.
friend who's a marine biologist who goes diving. So I guess she would have to have a very good lung. I don't know, whatever you physical part to do diving.
We'd have to be a good swimmer at least, but yeah,
Yeah.
that's true. And then you have, I mean, you have people like us who, I mean, I don't need much physical skill. I do my job. Maybe I'll come to regret that statement when I do my experiment at surf and everyone is telling me like, be prepared to have freezing hands. You know, I think that changes when you go into the field. And in fact, maybe Laura, you can probably speak to this. Did you have to do some programs beforehand, like so that you could save your life if something happened? Like I've heard of, so a group of
Yeah.
us, Arctic scientists, they spent another year in the Arctic Ocean, and to prepare for that, that was actually one of my advisors went there. She had to do all sorts of training where I think she had to jump into ice water and like free herself from something. And did you have to do that kind of
Wow.
stuff too?
No. For us, we were just on a boat for 3 weeks and they just gave us like regular boat safety training. But since I myself wasn't going onto the sea ice, they didn't give me sea ice training. So there would be training like that. But also I think like the modeling community is very accessible to all kinds of people. Like I think like body wise or anything, like if you're not a physically active person or you can't be going into the field because of maybe life circumstances, you have children or whatever, um, I feel like modeling is very accessible in that way, which is really nice.
And to that point, even now, a lot of observers can be landlocked observers now because there's so much we can learn from satellite measurements and also from these automated instruments that are measuring the ocean and just sending it via satellite. So there's a lot you can learn both about from modeling and from the real ocean, just sitting in your backyard anywhere in the world. And I think we're definitely tapping into that this year, all of us in the community, because we're so limited in where we can go. So everyone's really tapping into those data sets. But yeah, lots of different ways to
Yeah,
do this,
yeah.
and all of them
I
really
guess like
helpful.
I kind of have a question for you, Erica, and I guess I could share my screen because I know we're running out of at 15. Is that when we end?
I think that's what they said. I don't know if they're still
Okay.
here.
Yes,
I was
2:15.
curious. Okay, perfect. Erica, I was curious if like there was, I'll share my screen so we can get the slideshow back, but from this last year being in COVID, was there something that you kind of took away? Like I'll just put up this was kind of like our take-home messages from how the ocean, how ice melts ocean in different ways, where we had rising sea level, density of the water, and making it hard to mix ocean layers. But I think I'm just gonna switch to our last slide here.
Right.
Maybe if you just want to kind of talk about your quote, maybe.
Yeah, so this is something I didn't put the name here because it was actually a mentor of mine. So it's not a published quote, but that's for the, you know, for the mentors out there, if there are any, we are listening and taking notes. But I think this speaks both to science and to career development. Having the courage to be imperfect. Science is a telling of stories, and each story builds on the next. Oh no, my cat.
Oh, your cat. Yeah. And then for my quote here, I just say that it's not the destination, it's the journey, because throughout the way you look back on what you've done, and I've enjoyed this part. I don't know still where my future career is going to hold. Like I'm still in it, right? Like we're still going to be working for the next decades, several decades. But so far it's been a really great ride. So I'm just keep looking forward to what more can come from it.
Yeah, no, and I think my quote is kind of speaking to the same thing. Like, we don't know where it's going. Like every time you take a step, you don't know. And I think looking back at on where we've come and where I've gone, each step was very uncertain for me. I remember having these moments where a part of me every time was like, what did you get yourself into? But it's okay, I tried a lot of things, and some of them I loved and some of them I didn't like, but you learn something every time and you just keep building and it goes to the next thing and the next thing. And yeah, I think that really helps. And that's true of science too. I remember one of my favorite scientists giving a talk and saying, he was always very proudly saying that his PhD thesis was wrong. Like he was 70 years old at the time. He's like, all wrong, all incorrect. And that's true of science too. We try things and we try to be as true as we can to what we've learned and understand. And sometimes it works and we've learned something about nature, and sometimes it doesn't work and we learn something about nature still. So I think it's all kind of the same idea. We got a few
science isn't afraid to be, science isn't afraid to be wrong.
Yes, that's right. Science doesn't care. Nature doesn't care what we think.
Yeah, guys, I guess like we can kind of just say, ask us a bunch of questions until we run out of time, because we're here and we could keep chatting forever between Erica and I.
No, we'll just keep hanging out. And you guys are like, oh, I'm so bored of listening to you.
Yeah. But yeah, we both work at University of Manitoba through the Center of Observation Sciences, so CEOS.
Yep.
And actually, Erica and I are both in unique situations where I live in Edmonton, Alberta now, and Erica is in Toronto.
Yeah, that's right. Yeah, that's very COVID related, but yeah, we're with our families in different places, but we are part of U of M. We'll certainly be back there when it's safe to do so. I'm really excited to be there, especially over winter, to do an experiment at the CA's environmental research facility, SURF, the swimming pool we were telling you about. So we'll be back there soon. Yeah.
And do you know if there's any high school opportunities, like high school student opportunities within CEOS, maybe for doing like a taste of science or anything like that?
Yeah, that's a really good question. I don't know off the top of my head. I'd like to say it's likely. A lot of times we hear about these things just from a cold email. Like you could email somebody, go to the website, see if there's research that you think, oh, that's really cool, and shoot an email. It's very possible I'll be hunting for some high school students to work with this upcoming experiment. There might be a lot of kind of manual labor that will go along with setting this whole thing up. So I don't know yet, but I think it's certainly possible. So if you just go through and look, Google CEOS, CEOS, and University of Manitoba, you'll find profiles of all sorts of, oh, thanks, Laura. Yeah, you'll find profiles from all sorts of scientists, and that'll give you a sense of what people do. And just feel free to cold email them. Just say, hey, I'm really interested in XYZ. It looks like that's your thing. And you never know where that will take you. That actually got me my job at the Museum of Natural History in New York. I just graduated and I was like, hey, I'm looking for something to do for a year while I decide if I want to go to graduate school. You never know where it'll lead.
Like, yeah, stay curious and take all the opportunities. Like at one point I did an internship or like a fieldwork opportunity at a weather station, like at Environment Canada, just to see what it would be like to forecast for the atmosphere. And I quickly learned that I didn't enjoy that as much as my other friends who were doing it. So I was like, okay, tried it, tested it out, didn't like it, next. Like you just got to keep going.
Absolutely.
Yeah. Any more questions, guys? We're kind of gearing up towards the end. But I hope that this was encouraging for you guys to just like, even if you're not like, if you don't care about going into climate field, maybe you still care about the climate, but you want to do something else, just invent your job. Like I remember like thinking about the Day After Tomorrow movie, thinking like this guy is like a climatologist and he gets to talk to the government. I want this job. And I remember asking about this job, and a lot of people told me this job doesn't exist. You're making this job up. And yeah, that was so discouraging. But I remember thinking like, I'm gonna invent this job. It might not exist, but if like I was so stubborn. So I was like, this is what I want to do, and I'm gonna do it, and I'm gonna create this job. So I don't know. If you like something, just go for it. Just keep doing it.
Yeah, I totally agree to that. Just keep following your nose and following the things that you find interesting.
I'm sad that this is over.
Yeah, me too. That was fun. I hope this was fun for you guys. We certainly had fun hanging out with each other. But
Yeah.
guess we can't really know.
Yeah.
That's the fun, the weirdness of these virtual things.
I know. Yeah, that's why we did it a little bit differently by having Erica and I having a conversation instead, just so we can get a little bit more back and forth. Oh, good. Okay.
Thanks, Anna. That's really nice to hear. Thank you for coming.
Yay.
Oh, look at all the nice. We just had to ask.
Oh, yeah.
You guys are so sweet. I really appreciate your presentation style. Oh, that's really touching. Thank you.
Oh, nice. Yeah, we were hoping to hear what you guys thought about this, if you found this interesting, the way her and I had a discussion. So yeah, we're happy to hear that you guys enjoyed it.
The good and the bad, like I really appreciate these nice comments, but if you have suggestions too, that'll really help us because we really enjoy outreach and we might try to do this again. Thank you. Oh, that's cool. And yeah, with the experiments, please like go and play in your kitchen. It's super fun. Get some food coloring, play around with the amount of salts and the different temperatures. There's some craziness, and there are people studying this system, if you can believe it, and still trying really hard to understand it. You can get some really crazy fluid dynamics if you fool around with the ratio of the temperature gradient and the salt gradient. I do play with my kitchen. That's great.
Yeah. Add some oil. I feel like adding oil would just complicate everything too, because then you're like, okay, what happens if there was oil in the system? Like,
you know, there's people doing that at surf. They have, so I showed you guys the big pool, but they also have these kind of hot tub things, and they're playing around with oil and adding oil to it and seeing how does that change the CAs. And you could probably do these. I was thinking this year, I was almost like, maybe I should do a mini surf experiment outside on the balcony here, you know, because it'll be cold enough here, it'll freeze. And anyway, there's always
God, there's so much. Like we didn't even talk about like how people do biology and chemistry. We were just talking about like our side of things, but it's such a big world. Such a big world.
Yep. Cool. Thank you for the feedback, everyone. This was really kind of you.
Well, thank you for Laura and Erica for their presentation and their experiments. I know it was super interesting. And we'd also like to thank the students for joining us today for the final day of EnviroTalks. Feel free to follow LTS at LTS_U of M on Twitter, Instagram, and Facebook.
Cool.
Yeah, amazing that you guys came on a Saturday. Like you guys are powerhouses.
I love it. I love the enthusiasm. That's so great.
And finally, we also have a new podcast. It's called Let's Talk Science's Declassified STEM Survival Guide, and it's now available on Apple Podcasts, Spotify, Anchor, and more. Currently, we have the Farm Survival Guide series out now, and we will also be releasing the EnviroTalks webinars as bonus episodes on our podcast at the end of the month. We will also be releasing Med Survival Guide series next month, so feel free to check that out. You can scan the QR code if you're interested.